Hello, in today's video I'm going to discuss about the weight initialization in neural network. So weight initialization, suppose this is the neural network. These are the input layers, hidden layers, output layers. The input you get it from the input features. Then after that we have this weights W11, W weights for X1, W11, W12, W13, W14, weight for X2, W21, W22, W23, W24. When the network starts first, what should be the values of these weights? We don't know what should be the values, and there are certain ways to initialize these values. Okay, if these weights are not initialized properly, then it may lead the accuracy may not be correct, and it may lead to vanishing gradient descent and exploiting gradient problem. So it is very crucial to initialize this width properly to enhance the accuracy and to prevent the vanishing gradient descent and exploiting gradient problem. Let's see what are the types we have in weights initialization. So weights initialization. So let me put first we have zero initialization or constant initialization. Then the next there is random initialization, where it will initialize random number. So there are two different kinds in this. For uniform distribution, there's one formula. For random distribution, normal distribution, there's another formula. Okay, then the next we have Javier or Glorard initialization. This also similarly, there's a random, there's a uniform, and there's a normal. And uniform is for uniform distribution, normal is for normal distribution. The next we have he initialization. These also have two types, he normal and he uniform. The next one we have the orthogonal initialization, and lastly we have Bayesian initialization. Okay, let's go through in details each of the initialization process. Okay, before we proceed to the different initialization models, initialization process or technique, we need to know this. In a node, these are the weights which is coming in, and these are the weights W01, W02. These are weights coming out. What do we call this? WI input 1, W input 2, W input 3. These are called fan in inputs. Means the inputs going towards the node. And W01, W02, these are called the fan out. Means the ones which are going out of the node. So here we can say there are 3 fan in and 2 fan out. Normally most of the technique uses this number of inputs. What is the number of inputs, fan in inputs, and the number of fan out? Okay, so first is the zero initialization, or some people call it constant initialization. So these are the, it will initialize all the weights to 0, w1, w2, w3, whatever is it will initialize everything to 0. Okay, so this is a simple code in TensorFlow. We just initialize, we use the initializer and then put it in the layers. So what are the advantages? The advantage is pretty straightforward, just initialize everything to 0. Okay, and another results are also not varying, hence reproducible across all runs. Means like if we initialize everything to 0, you run it, you stop, and then run again, it will be the same. Okay, then what are the disadvantages? Disadvantage is like, since we initialize all weights to 0, sometimes it's not learnable. You will not be able to, it will not be effective. Okay, every time initialize to 0, it probably is going to be same. The layers on the top and the layers on the bottom, it may not have differences. Okay, so it is just there's a symmetry. It can lead to vanishing gradient descent, and gradients for all fit being same could not lead to no learning at all. Yeah, so these are the advantages and disadvantages. Then random initialization. In the random initialization, it will initialize the weights of the network to some random value except 0. But here there are two kinds, the normal distribution and uniform distribution. Normal distribution range from 0 to some standard deviation, 0 to uh, standard deviation value, whereas for random it will range from low to high, which we can say it is a minus value to the plus value. So here you can see for a normal distribution, for the normal distribution oh sorry for the normal, it ranges from 0 to standard deviation. What is n? N is normal distribution. 0, what is 0 is the mean, and the standard deviation is calculated by square root of 2 by fan-in, number of fan-in values. Okay, then how about the random uniform? Random uniform is from low to high value, probably minimum to maximum. So u means uniform distribution. What is a low value? Low value is minus of, this value is going to be same, it will just have plus and minus. The minus of square root 2 divided by number of fan in inputs plus number of fan outputs. Okay, if we add up those two, and it will be the low value will be the minus and high value will be the plus value of that. That's why fan in and fan out is very important. Then we go to the next. So this is a simple code for normal distribution here and for uniform distribution. Here you will see mean and standard deviation. So mean and standard deviation, those are the two values we use for the uniform, and for the normal, and for the uniform we have minimum value and maximum value. Here we specify, here we are not using the fan in fan out, here we just giving an explanation of how we can use. So instead of mean and standard deviation, you can input the value which you derive. Similarly, minimum and maximum, you can use the value which you derive from here. So what are the advantages? The advantage is like, say it prevents the symmetry which was created due to the constant or the zero initialization, and for since it has the different weights, random different weight, it is less likely to get stuck in a local minima, and the next is it has a faster convergence. What are the disadvantages? Disadvantage is if you don't initialize properly, if you don't select the value, if the value which it uses is not what it is poor, or it may be it mean it's how do I say, it is not in a proper way, it can lead to very slow convergence. It can sometimes lead to overfitting, then it's hard to reproduce as different runs reproduce different results. Means like when you do first time you run, it will be some random value, then you try to test something like test like repeatability, something kind of thing. You run the second run, it may be result is going to be different, it's never going to be same, unlike the constant and the zero initialization. Okay, that is one disadvantage. And if you don't if the values are not initialized properly, it can lead to very slow conversions. Okay, go to the next one. Xavier and Glorard initialization. It's it helps to prevent the vanishing and exploiting gradient descent which we face in the zero initialization or constant initialization. Here also there are two kinds. One is for the normal distribution, the other one is for the uniform distribution. Same. The formula, the technique is the same. It will have for normal distribution 0 to standard deviation. Only thing is like the standard deviation formula is different. Standard deviation here for the normal distribution is square root of 2 divided by fan in plus fan out. So here in this, fan in plus fan out will be 3 plus 2 in for this particular node. So here, and for the uniform, the value will be square root of 6 divided by fan in plus fan out. So it will be the lower will be the minus of value, high will be the plus value. So we go through the code, we use the code. So here we can use in TensorFlow using this initialization. There is a Glorad normal and then Glorad uniform. What are the advantages? Advantage, it maintains the variation of the activations and the gradients throughout the layers. Okay, and second one, it balance variance often leads to faster conversions. Okay, this is there, and it improves the performance. And what are the disadvantages? The disadvantage is it may not perform well in activation function like ReLU. Okay, where the node uses activation ReLU activation function, it's not going to be it will not perform well. So it might not be the best choice for all the network. Okay, all the network we cannot use Glorad. Okay, we may sometimes we may need to use ReLU, sometimes we may need to use he. Sometimes we may need to use a he uniform. Okay, we go to the next. The next is he initialization. So this initialization is particularly suited for network using ReLU activation function. ReLU tends to zero out negative input which leads to the loss of variance. Give me a minute. So what it means is like here ReLU and the ReLU, if we have value something like this, so under ReLU what it will do is all this negative value will be zero, or maybe it will be like this, and then it will do like this. So this value ReLU means it is the ranges from 0 to maximum value, 0 to infinite value. Whichever is less than 0, it will be 0. Yeah. So all this will be 0 out. So this is what he mean. Okay, and then here there are two kinds, same he normal, he uniform, the same formula. Only thing is the formula is different. Square root of 2 divided by fan in for normal, and for uniform square root divided by 6 by fan in. Okay, so here is how it's being initialized. you see normal here, uniform. Okay, so what is the advantage there? It mitigates avoids the vanishing gradient issue and exploiting gradient issue. Okay, and this is specifically designed for ReLU activation function, and it preserves the variation of the activation function across all layers, similar like the Javier and Glora. Okay, what is the disadvantage? This disadvantage is designed for feed-forward neural network may not be effective for RNN or CNN. Without much modification, we may not be able to use in RNN and CNN. Okay, and what about it is effective for ReLU activation function, but it may not be effective for sigmoid or tannite. Okay, I move to the next. Orthogonals initialization. What are these orthogonals? These are initialized in such a way that they form an orthogonal matrix. Like, so here we need to know two terms here, orthogonal to each other, sorry, orthogonal to each other and have a unit norm. So orthogonal in the sense that it is if you have a matrix where the number of rows and number of columns is going to be same, so it's going to basically going to be square matrix. And suppose this is this A is a matrix, A is a matrix. So orthogonal means when you multiply these two matrices, dot product of this A and A transforms is going to be an identity matrix. Okay, is some match. Identity matrix means where all the diagonal values will be 1. Okay, so it is some match. So what are the advantages? By preserving the norm of the gradient, orthogonal helps to ensure that the gradient never vanishes or exploit during the backward propagation. So it prevents vanishing gradient descent and exploiting gradient during the backward propagation. And also it helps to maintain the stability of the signal as it propagates through the layers of the network, and it improves performance and obviously faster convergence. Okay, then what are the disadvantages? Disadvantage is creating this matrix is going to be very computationally expensive, especially if it is a very large network. If it has a very large number of nodes, we need to create this orthogonal matrix for each of the nodes. Yes, and it also depends on the number of the nodes increases, the number of inputs output increases. Eventually, we need to calculate a lot of orthogonal matrix, and these are not very much suitable for uh, convolutional network. Okay, the next. So this is for, we can take this as an example. We have input, we have different kernels, we have weights, then we will have this input and weights w1 w2 w3. So this is, suppose, see, these are the, say these are the orthogonal matrices. So for each of the input we need to have the orthogonal matrix. Say this is a kernel or the weights. So a simple example is this, not very good example though. We have a random input here, we get a matrix and then the dot product of the matrix. Okay, go to the next. Lee-Chun initialization. So these are basically used for exponential linear units. scale exponential linear units, and this can also be categorized into two, one for the normal and one for the uniform distribution. Same method, only thing is the difference is here standard deviation square root 1 by fan in, and for the uniform distribution, from low to high, the value is determined by square root of 3 divided by fan in. Okay, let's see how it's being implemented. So you need to use the initializer, lesion normal, and then you can use in the layers. For the uniform, similar things, and then you can use in the layers. What are the advantages? Yeah, same like previous, it provides stability by maintaining variance of activation and gradient, suited for networks using sigmoid and 10H. Okay, and not for ReLU. Okay, which are sensitive to the scale of input weights, and it reduces the vanishing gradient descent and exploding gradient problem. You need to know these two. It is suitable for sigmoid and 10H. So what are the disadvantages? It is not suitable for ReLU, and it is very sensitive to hyperparameter number of inputs and may not be suitable for deep networks. If the number of input is too much, so it may not too many, it may not be suitable. Okay, simple summary. Where do we use JV and Glorad? We can use in a non or hyperbolic tense, sigmoids, softmax. How about the He initialization? He initialization is used in rectify linear units and its variants. So ReLU has many variants, namely liquid ReLU, parametric ReLU, or exponential linear unit. Okay. How about lesion? Lesion is like we mentioned earlier. It's used in scale exponential linear unit. Take note of this. Where we can use what type of initialization functions. Okay, that's all for me today. Thank you.